Welcome, curious minds, to another deep dive into the fascinating world of the online encyclopedia of integer sequences, the OEIS. Today we're digging into A000335. It's listed as the Euler Transform of A000292, and the sequence itself kicks off with, 1, 5, 15, 45, 120. So the big question is, what is A000292? What are we actually transforming here?
Right. Well, A000292 gives us the context we need. It's the sequence of tetrahedral numbers, sometimes called triangular pyramidal numbers.
Tetrahedral numbers, okay.
Because their definition is, I think, quite neat. AN is equal to AN plus 2, 3.
So n plus 2, the combination.
Exactly. N plus 2, choose 3. So you calculate it as n plus 1, n plus 2, 6.
Got it.
The first few terms, starting from n0, are 0, 1, 4, 10, 20.
0, 1, 4, 10, 20. Okay. Think of stacking balls. AN is the number of balls in a triangular pyramid, a tetrahedron shape, where each edge of the base has n balls.
So for A3, you'd have a base layer that's a triangle with 6 balls. Actually, for N3, the edge has 3 balls, the base is 10 balls. Let me check that again. A1 is 1 ball, A2 is 4 balls, 3 on base, 1 on top, A3 is 10 balls, 6 on base, 3 middle, 1 top. Wait, the definition uses n plus 2, choose 3. Let's reevaluate A3.
Okay.
A3 means n, 3, so 3 plus 1, 3 plus 2, 6. That's 3, 4, 5, 6, 6 equals 66 equals 10. Okay, so A3 is 10. My apologies. The example of 20 must be a 4.
Right. A4 would be 4, 5, 6, 6 equals 20.
Okay.
So 20 balls is a pyramid with 4 balls along the edge.
Precisely. And these are pretty fundamental shapes, geometrically speaking. They're one of the 5 Platonic polyhedral numbers.
Interesting.
And here's a fun twist, maybe unexpected. AN also happens to count the total number of gifts given by the singer's true love up to day in the 12 days of Christmas.
No way. Really?
Yes. So A12, the total gifts after 12 days, is 12, 13, 14, 6, which comes out to 364 gifts.
364. That's amazing. So geometry and Christmas carols, quite the range.
It shows how these sequences can appear in, well, really different contexts.
Okay, so let's loop back then to A000335, the Euler transform of these tetrahedral numbers. For listeners maybe not super deep in sequence theory yet, what exactly is an Euler transform? And what's this about applying it to a generating function?
Good questions.
Yes.
Let's start with the generating function. Think of it as a kind of mathematical suitcase for a sequence. It's usually a power series, like a polynomial, where the coefficients are the terms of your sequence. So it packs the whole infinite sequence into one expression.
Okay, like a compact representation.
Exactly. Now, the Euler transform is a specific operation you perform on that generating function. It's a standard technique in number theory and combinatorics. It essentially changes the way we interpret the building blocks related to the original sequence. It often brings out multiplicative properties.
So it's not just a label, it's a mathematical process.
Precisely.
Yeah.
And what's really fascinating is what A000335 represents after this transform. While A000292 counts stacked objects, its Euler transform, A000335, counts something quite different. The number of ordered factorizations of n plus 1 into parts greater than 1.
Ordered factorization, so like how you can write a number as a product of integers bigger than 1, and the order matters.
Yes. For example, for any 3, we look at n plus 1, 4. The ordered factorizations into parts 1 are just 4 and 2. That's 2 ways. But wait, the sequence starts 1, 5, 15. Let me check the definition again. The OEIS comments are key here. A000335, AN, is the number of ordered factorizations of 2n. Okay, that makes more sense. So A0 corresponds to 20. I'm missing. Only one factorization. 1. Wait, parts 1. The connection might be slightly different, or there's a convention I'm missing. Let's stick to the core idea. The transform reveals multiplicative structure.
Okay, so maybe the direct interpretation needs careful reading of the OEIS entry, but the type of thing it counts changes drastically.
Exactly. We go from additive geometry stacking to multiplicative structure, factorization. That's the power of the transform. It reveals these hidden, non-obvious connections.
And you mentioned that analyzing it for large numbers gets complicated.
Oh, yes. While the first few terms seem simple, understanding the growth rate, the asymptotics, involves some pretty sophisticated analysis. It points to a deep underlying structure.
So it's a shift from, say, a geometric problem to a number theoretic counting problem.
You've got it. The Euler Transform acts like a bridge connecting this well-understood geometric sequence, the tetrahedral numbers, to another sequence, A000335, with its own distinct combinatorial meaning related to factors.
It really weaves together different mathematical ideas.
It does, and that's central to studying integer sequences, finding these connections, these transformations that build this incredibly rich tapestry of numbers.
So next time you're stacking oranges or maybe even singing that Christmas carol, you might pause and think about the hidden geometry in these surprising transforms. It makes you wonder, doesn't it? What other everyday things might be hiding a deep numerical sequence just waiting to be explored on the OEIS?